It is because I posted the solution key.
Oh, you did?
Yeah, I'm sorry. Good morning.
Good morning.
How's everyone doing?
Good.
It's here. Okay, good. So, any non-hurricane related questions first? No, everyone's good as far as the non-hurricane stuff. That's good. See, this makes calculus not look so bad, you know. So, hurricane-related questions. So, here's the deal. A couple of things that are important that you should know. The first is that nobody knows what's going to happen. Okay. The other thing is that if you do have to evacuate the hurricane, my own personal experience is that it is really hard once people actually know what the hurricane is trying to get out of the plane. It's almost impossible. So, if you have to leave, that's fine. What I'm doing right now actually is I'm making a screencast. I'm making a video of the lecture so you can follow along. Unfortunately, the audio, if I talk really loud, it's not going to make me or hype or anything. The audio is not really great, so I'm going to try to stand next to the computer and just pick it up. And I'll post the video. So if you're not here Thursday, you're not here Friday, you won't miss lecture. I do expect you to watch them. We're going to try to stay on schedule. We'll see what happens, okay? Most likely, if the hurricane does hit, it's going to hit Monday. That's when we're going to be most effective. And of course, you won't be here to turn in homework, and we'll jump off that conclusion right forward. But try not to worry about that. We will be okay. If you're not here, you can't turn it in. So we won't worry about that. I have a few non-hurricane related announcements. So let's see if I can pull them up here. So just a few things really quickly that we need to touch base on. The first is the homepage. So I've redone the Canvas homepage. Here's a few things that you might want to check out if you haven't seen them yet. I have the syllabus on there like before. I have the tutoring office hours. Okay. And so now I have the hours for the SI. That's the person that's going to be there for evening work. And I also have my schedule too with the SI. So the hours that I'm going to be there, okay? So if you click on that, it should bring up a PDF. And it'll show you when the hours of the regular tutoring center are, okay? But it will also show you the hours for the SIs too, the evenings. And I'll be there actually tonight. Okay. The last thing is, the assignment. So from now on, I'll start posting, as soon as you turn in the old assignments, I'll post a new assignment. Because every once in a while, we're going to have these things where like, the problems is that you kind of want to push over to this section, okay? Or the hurricane things can change. Just do the hurricane update. If you need any announcements related to that, I'll post on it. In this assignment. Yes, sir. So, and you know, honestly, I don't know the answer to that question. I wish I could tell you, but I don't know. I'm sure that there are policies in place, and if that happens, one thing I will say is this is really good at, doing that in place. So we will get it right. But that's the reason why I'm doing these lectures now, so that we can really kind of minimize any further questions. All right, other questions?
Just a comment. I know most of you are freshmen and you're new as well. Last year for Matthew, we lost one day of school and they added it on at the end of the semester. We usually have a study day at the end of the semester, which is just a day off to study for the whole finals. They took that away from us and made an extra day of class. So that's what happened when we evacuated last year. But they'll add on what we missed, what they canceled classes for.
All right, good deal. All right, so what we want to do now is I want to go into section 2.3, and we didn't finish it up because we have to do the limit theorem. So section 2.3 is talking about how we evaluate limits. So we have all these limit laws, properties of limits, right? If the limit of two functions exists, their sum, their product, their quotient exists. Now we want to deal with a situation that's kind of interesting. This is called the Squeeze Theorem. And so I want to discuss what the Squeeze Theorem actually says. And sometimes the Squeeze Theorem is called the sandwich theorem. I'll show you why. Both are actually really good terms. So here's what's going on. I'm not going to really bother with this theorem up here. I'm just going to go right to the Squeeze Theorem. That's the theorem that you should look over. But what we're going to be interested in mostly is this. We're going to say, suppose we're interested, so here's what I want. I want the limit as I approach a point of some function g of x. That's what I want to find out. And I know something. I know that there are two functions that bound g of x. There's a function that bounds it from above. In other words, it's always greater or equal. That means the graph lies above, right? So this is that function h. And there's a function that also bounds it from below. In other words, she can't go below this other function. That's what a bound is, right? So this is always less than or equal to g of x. So we know this piece of information. H and F, and H bounds G from above, and F bounds it from below. And so F bounds G from below. There's one little condition I have to have, which is I'm interested in this condition on some little region around the point that I'm Notice it isn't true for everywhere, right? Here G goes above H. But I want to say I just need some little neighborhood of A. In other words, think of neighborhood like it's the point where A is using where A is, right? So there's some little interval, I'm going to call it the neighborhood, where this is true. And I'm going to say this is true on this neighborhood. Okay? And because it's a limit, we don't actually have to worry about what's going on at A. So we can sometimes we call this the deleted neighborhood. In other words, we're not interested in the person below me. So if this is true, this is the sandwich part of the sandwich thing. Because this tells me that in some little neighborhood of A, that function I'm interested in, G, is sandwiched by two other functions, right? Apparently it's sandwiched. Here's why it's called the squeeze theorem. Because there's one last piece of information we have to know. We have to know that the limit of H and F converge to the same value at A. So we also know that the limit as x approaches A of f of x is equal to the limit as x approaches A of h of x. And notice why that's important. And we're just going to call it capital L. We generally call limits the y value we converge to capital L. And notice why this is called squeeze theorem. Because that guy G didn't want to sandwich between them, but as x approaches A, what's happening? Those two functions, they're converging to the same limit, right? They're coming together and they're squeezing G, and they're forcing its limit to also be the same. Okay? So if all that is true, then we can conclude what we get is we get the limit. And so G of x has to converge to the same value. That's the squeeze part of the squeeze thing. And it's probably called other things, but the sandwich theorem and the squeeze theorem are good. Okay. Notice there's a lot of work you have to do. You have to find those two functions, and you have to know that they converge to the same value. And so that's not given to you in the problem, right? So let me just kind of show you let me illustrate how it works. Are there any questions though on the theorem, what the theorem is actually saying? Okay. So and I'm going to change this problem a little bit if you don't mind. I'm going to look at the limit as x goes to 0 of this function, x times sine of pi over x. So, that's the limit I want. And I know this function here is crazy, sine of pi over x. In fact, here's a little MATLAB plot. That's just playing around having some fun. Here's the MATLAB plot of sine pi over x. See that blue thing? As it converges to 0, is it converging to anything? No. If it was converging going to a value, it just keeps oscillating no matter how close. This is 0.05 to 0. You can get as close as you want. I'll put the MATLAB play around. Make it between minus 0.0000001 and do the same on the other side. You'll see the same thing. And in fact, they'll get worse. And after a while, your computer won't even be able to do it. So this guy, we know the limit doesn't exist. But what about the product of those two? So let's ask a question. What's the point I'm converging to? I'm converging to x goes to 0, right? In the neighborhood of 0, do I know two functions that bound this function? So, here's one thing we know. This thing behaves weird, but it's bounded, right? Sine of pi over x is bounded between what? What's the values of sine between? 1 and -1. So this is bounded. I'm just going to write b d d if you don't mind. That's how we write positive now. Between -1 and 1. What happens to the limit of x as x goes to 0? So what do you think the bounding functions might be? What functions do you think bound is? Sine and negative sign won't work. It's a good guess. So here's where I'm going with this. Here's what I know. I know this is true. Pi over x. This is true for all x not equal to 0. Okay. What do I want? I want x sine pi over x. Do I multiply 2 by something? Notice how hard this problem is. This is not easy figuring out this bounding function. So we're going to come back and we're going to work some different tricks. Calculus is like a video game, right? You get to different levels. How do you get to the levels? You learn little tricks, right? Like that. Something here. How do you get these two functions? Well, there's certain things we're going to say. I'm gonna give you the answer because it isn't obvious. The answer is to multiply through by x. Now I got my bounds. And if I really want to be careful, I should multiply through by the absolute term. Or I should multiply through the absolute term. But then this way. And these are my two functions. So what I know, I'm not done yet, but what I do know is that near 0 there are two functions that bound me, right? Do I know the limit of these two functions as x goes to 0? I know that they're both 0. So I can use the squeeze theorem, okay? So I got my two functions. This is my, what are we calling it? F. This is my function f that bounds from below. This is my function h that bounds from above. And I know that the limit of each of these as x goes to 0 is 0. Now I can use the squeeze theorem. So I have my bounding functions plus I know that the limit as x goes to 0 of minus x is equal to the limit as x goes to 0 of positive x. So now I can use the squeeze theorem. So what's my answer? These two guys are squeezing it to 0, so what must it be? 0. That's it. So now I know this limit. And that is my answer. Cool. Squeeze theorem is powerful, but it also makes more work. So let me just show you a picture, if you don't mind. This is what I did on MATLAB. It's easy. I'll post the code. It's a piece of cake to do. X. Run this. This is the function. And sometimes in physics we call this envelopes. Okay. So this is the lower envelope. This is actually, if you want to do both, this would be minus the absolute value of x. This would be positive the absolute value of x. And you can see it's happening in function versions. Even though it's oscillating, the point is that the amplitude of the oscillation is modulated. How would you know to do this? So you see this on an exam. So here's some little tricks here. So here's some tricks for us. When we have the limit of x goes to 0, and we have any power of x, okay? It can be any power of x. So this can be a root, an exponent, as long as the exponent's positive, okay? Positive exponent, doesn't matter. anytime the exponent's greater than 0, and you have any function that's bounded in an interval around 0, we don't care about 0. Notice that in that sign of pi over x, we can't even talk about 0, okay? But as long as it's bounded in the neighborhood, okay? So it's bounded in the neighborhood of 0. We write neighborhood NBD. Is that okay? What is that limit going to be? Well, use your imagination a little bit. You can convince yourself that's going to be 0. This is always going to be 0. That's the most common line. All of the problems basically in the problem. Suppose you don't see that. The other trick is that if you have a sine or a cosine, you always want to start with the fact that the sine and cosine values are bounded by plus or minus 1. That's where you start from. And this can either be sine of x or cosine of x. Okay. I'll write on side. Either one of those. That's generally where we start. Use that fact. But generally, we're not going to do it. If you remember the first one, 95% of the time, you're not going to do a lot of the things. Because there'll be a lot of things where, notice, for example, could I use the product? Well, this is going to get confused. You say, well, I have a limit of the product, and when you look at the form, right, the limit of the product is applied to the limits. Will that work in that class space? No. The limit is some kind of the limit of the product. That's how you can kind of sort these things. Have the product, and you can't use the product rules, you can ask yourself, can I work with that whole thing to find the function? Little tricks. And that's why you get paid the big money, because you learn all these tricks. How do you learn? Practice. You learn by practice. Okay? Questions on the Squeeze Theorem? Everybody's good on it? Alright. And I think all the homework problems are of the first type. I'm 90% sure. Alright. So we want to switch gears a little bit and talk about something different. We want to talk about continuity. So this is the next section of notes. So one of the things I did, I don't think I mentioned this in class yet, is that notice that I'm breaking the notes up into subsections. And there's kind of a reason why. I like this book. Quite honestly, I wished I had this book when I was a calculus student. I think it's an exceptionally good book. It explains all the little things that can go wrong very, very well, I think. The one thing that can be challenging about that, though, is it's a blessing and a curse. So you have all this information, but one of the things that I think can happen is sometimes people get. And it's hard to figure out how the other words figure out all this stuff. You're going to try to group these things. You may find that the order of the things in the notes are a little different as the chapter, but I'm trying to kind of combine them so that it's okay? All right, continuous functions. We're going to deal with continuous functions a lot. They're very important. So let's kind of go through what we're talking about. It's really important to understand two things. There's a difference between continuity or function and continuity and a function or function. And it's important to understand what discontinuity is. So let's just start with continuity at a point. And I'm going to emphasize this, okay? So the definition, the formal definition is that if you have some function, and the limit of that function as x goes to a is equal to the value of the function at a, it's said to be continuous at the point a. Okay? And I'm just going to emphasize this again. Now, I'm going to be honest with you, continuity was something that when I was a student, I don't think I really got. I mean, I used calculus, but honestly, when I look back and I'm working with it later after graduating, I remember one day I kind of found a dream in the cars. So I want to try to explain it to you so that you get it. So notice what it means for a limit to exist. A limit to exist in a thing like a car crash means the two cars are traveling along the graph, and as they approach the same x-coordinate, they approach the same y-coordinate. We never said they got to it. God intervened at the last moment to stop it. Okay? We never actually get it. What it means to be continuous is that the cars crash. Not only approaching the crash site, but they actually get there. They converge to the same y-coordinate. That's one way of thinking about it. The way that I've seen a lot of students taught is this thing called the pencil test. So here's what the pencil test says. The pencil test says, if I want to see if a function is continuous at x equal to a, what I do is I start on one side of the function. I'm going to start in the graph. And I'm going to see if I can go to the other side of a by staying on the graph without lifting my pencil. So the goal is, I want to see if I can get to this side by staying on the graph and not having to lift my pencil. I can do that, right? I can stay on this graph, stay on the road, and I can get to the other side, past that x-coordinate. If you can do that, it's also continuous. So notice that, for example, I can't do this here, right? If I try the pencil test, I'm going. Oh, I can't get to the other side because there's a hole in the road. That's not continuous. All right. So let's look at this problem here. This is a problem that we had kind of like for homework. So we're looking at this limit problem. Let's just review how we handle it. So what made you come to that thought? That's right. I have a ratio. The hardest limits to evaluate are going to be the limits of ratio without a factor. You have this limit of the ratio. The first thing you want to know is the denominator going to zero? The first question we always ask, and it is. So then your second question is exactly what you said. Can I factor the top polynomial so I can cancel that nasty x minus 3, and then I don't have a problem? Okay. So there's a thought process. What do I have? I have a ratio, and I have a ratio of polynomials. So check that the denominator is equal to 0. And it is. By the way, I should do one more step before I go to factoring. What should I actually do? If it doesn't, factoring is not going to do any good. What's going to happen then? What would happen if I change the what factor? What factor of factor x? What's going to happen in that way? So here's the question. As x approaches 3, what's x minus 3? Real very small, right? So what's happened then? What's the effect of the denominator? What's going to happen? The function is going to blow up, right? And if I see that x approaches 3, the numerator goes to a fixed value, right? We know what's going to happen. So you're going to be positive infinity, negative infinity, right? Or it's going to be like this. So before you put the time in the factor, and although these aren't hard to factor, I would check if the denominator goes to 0. I'm going to let you do that. Do that as an exercise, and I claim it does. Now we worry about factoring. And by the way, factoring might not work. Okay? You could get two factors, and if neither one of them is x minus 3, you're in that same boat, right? Positive infinity, negative infinity, or it doesn't exist. But it just turns out that it does. So we're going to factor the denominator. And of course, what I'm going to do is I'm going to start guessing x minus 3. because that's what I want, right? I want x minus 3 to be in there. So I'm going to see if I can factor this so that there's a factor of x minus 3. And I say, oh, would this work out if I had x minus 3? Yep, that'll work out. Now I'm going to look at my limit. The limit as x goes to 3. And I'm going to put the factored form of the numerator in. And I cold-bloodedly did this because these guys are going to cancel. But wait a second. Can I cancel them? Are they canceling 0 to 0? No? But why isn't this 0? So as I'm approaching, those two things might get incredibly small as you want, but I'm saying they're not zero. So it's value. You're going to think about these things, okay? Now I get the limit of x plus 1. And I can do that. That's 4. The limit exists. So notice that for the definition of continuity, the limit has to equal the function value. If the function is not defined, it's not going to work. So the function is not even defined yet. Good. Most people miss that. So the answer is no, because f of 3 is not defined. What that really means is exactly what Austin said, that there's a hole in the graph. A hole in the graph means not. We can fix that, and there's just one hole we call a removable discontinuity. The way that you deal with that is you just deal with the function. And you say it's the old function, when x is at 3, and then when x is equal to 3, you put the value of the function. Okay? Define. Believe it or not, by the end of the semester, you're actually going to be able to read that. Believe it or not. Okay, so questions about this. So notice something really nice. There's a really important consequence in this. Is that when we have ratios of functions and we look at the limit, there's a value that makes the denominator equal to 0. The function cannot be continuous. Even if this continuity, even if this automatically denominator is 0, that's going to be an important effect. All right. So here's kind of the tricky part here is that sometimes it's easier to think about all the ways in which a function can be discontinuous. So how can a function be discontinuous? What does it mean for the limit to exist? It means 3 things, right? Anybody want to tell me something? It means that there has to be a limit as I approach the point from the right. There has to be a limit as I approach the point from the left or below, and they have to be equal. There's actually 3 conditions in that one statement. Okay? The function has to be defined, and the limit has to equal the value of the function. Can anyone give me an example of a function? Can anyone give me an example of a situation where the limit exists, the function is defined, but the limit's not equal to the value of the function? Right, that's the idea. So you want to kind of have these ideas in your mind. So correct me if I'm wrong, but I think what you're saying is there's some point where the limit exists. What does it mean for the limit to exist? It just means that 2 curves have to approach the same point, right? So this is going to occur, and then what's going to happen? Exactly. These things can go wrong in a lot of different ways, okay? All right, so let's look at this example. This is an example that's really similar to the last problem we had, right? It's a ratio with this removable discontinuity. Let's look at the conditions. Does the left-hand limit exist? Which one first? Does the right-hand limit exist as I approach 2 from above? Yeah, right? This curve is approaching a fixed value. I don't know what it is, but sure, it exists. Same is true that the limit exists from below. So therefore, if the limit exists from below, they're the same value, the limit exists, right? What about the function? Is the function defined though? No. This is exactly this problem that we had last time. And here's the thing, we only need one condition to go bad. As soon as one condition is not satisfied, all bets are off. It's not continuous. It has to do all 5, okay? Let me emphasize that. You have to have all 5. So this isn't like 5 and choose 4, okay? I'm going to let you play around with the other ones. I'll leave some of the other ones for, well, we'll do, let's see. Why don't we do this one? Okay. Well, let's just kind of look at this and ask, what goes wrong? Okay, if you look at this is like a function, right? Maybe 1 over x squared, right? What goes wrong with that function? Right. So there's a subtle thing that's not really important. Is that when we say the limit exists, we're talking about the limit approaching a finite value. So you might say, yeah, the limit exists. It's infinity. Yes, it is. It's not really infinite. When we say the limit exists, we do not mean that the limit goes, that the limit is infinite. It's a little bit of a weird changing thing. So here, we have infinite limits, but what we need for this situation is we need the limit to be finite. Now, if it now suppose you didn't know that and you kept going on with the problem, where would it fail? It definitely fail one place. Suppose you said, I don't know that. Well, I don't believe it. I think it's okay to something's still going to screw up. No, this problem actually 4 is okay. You might have a hard time seeing it, but the function is defined as 1. The function's actually there. But what can't happen? Yes, sir. No. As x goes to 0, this thing's going off to infinity. It can never go wrong. So even if you didn't know that, you're still going to be able to figure out that it's going to fail. The last condition's going to always fail when you have an infinite limit. Let's see. This is a cool function because it fails everywhere. That sign of pi over x, every single condition it fails. Right hand doesn't exist, left hand doesn't exist, the limit doesn't exist, function not defined. So it's like the nastiest function that you can do, right? This is a kind of cool function. This is a function that you use when you're looking at how much you paid to mail a package at the post office, right? Kind of has this. We have a name.
Piecewise function.
Say it again? And it looks like a bunch of strings. Right? So the postal rate's a certain amount to a weight, and then it's that function. So at 1, what condition is not satisfied? At x equal to 1. So the big question you can ask is, does the limit exist? The limit of the function exists at x equal to 1. Because this one, the left side limit, the limit of the lowest conversion is 0, the limit of the lowest conversion is 1. Okay. Now, why do we go through all this work? Why is continuity such a big deal? Okay. Well, it's because continuity is going to let us evaluate limits. We're going to see it's a really nice tool. All right. This part is a little tricky. I want to go through this kind of carefully, if you don't mind. So, remember I said at the beginning there's 2 things about continuity, and one of the things about continuity is a distinction between continuity at a point and continuity on an interval or a region, okay? So let me go through that. I want to erase last class notes. So. Any questions about continuity at a point though before we go on? It's very important. Right. So now we're going to talk about continuity on an interval. So by interval, we're talking about what some people call a connected line segment. Okay? Hold your number line, open interval, and so here's what we need to be continuous on an interval. At every point that has to exist in the interval. So let me be really careful about this, and I'm going to try to make this concrete. So let's go ahead and look at some interval. I'm just going to call it the interval AB. And I'm interested, when we're talking about intervals, we're almost always talking about closed intervals. And we're going to see why. There are a lot of theorems in calculus that only apply to these functions. Closed intervals. So now, those little brackets at the end, those mean that each one's taken included. So this is what we're saying. I'm looking at this right here. Okay? What I have to do are two things. First, I'm going to look at the interior of the interval. So the interior is everything except the endpoint. And I have to be continuous at all the interior points. And so this is the first condition. So, and I'm going to be a little more careful here. So this is every point in the interior, which in this case is the open interval AB. So I'm going to look at this interval first. And I have to be continuous at every point in that open interval. This is what I'm checking. Right hand interval, left hand interval. I can't play this game because we don't have the one-sided limit on one side. So B does not have the right-sided limit. I don't know anything about the functions outside of that limit, but I exist. So what we're going to do is we're going to check for what we call one-sided continuity at the endpoints. So let me be really careful about this. So what I'm going to do, this is the first step. The second step is I'm going to check for the one-sided continuity at A. And here's what I need. I'm going to abbreviate continuity CONT. That's okay. So what do you think one-sided continuity means? If continuity means that the limits equal to the function down, what do you think one-sided continuity means? Seems that one-sided limits can be equal. That's all we're saying. So the limit that exists here is going to be the limit as I approach A from above, I'm sorry, with a little positive sign here, right? F of x is equal to f of A. That's what one-sided continuity means. Because this is the only limit I can check, right? I can check the value, I can check the limit of the function, as the code of the function. And for the one-sided continuity is. And really, when you think about it, it makes sense. There's one wrong to approach A, and you end up with the next one. The other endpoint's the same sort of thing. Except where am I approaching? I'm approaching from above or below? So B, I'm approaching from below. Okay. So I'm just going to put little one-sided continuity at x equal to B. Same deal. Now, we didn't talk about one-sided limits a lot, okay? So I'm just going to make a statement. They're exactly the same as other limits. In other words, all of the limit rules that we have, the way they apply to one-sided limits. You treat exactly the same. The thing that you're usually watching is the sign. That's really the same. So, can we do this function here? Let's go ahead and try this function. So I want to see if it's continuous on the closed interval -1 to 1. And I don't want to draw a picture. Okay? So the first step is I'm going to ask, is is it continuous on the open interval minus 1 to 1? How do I do that? How many points do I have to check? I check 0, a half, minus a half. How many values do I have? It depends on the computer, right? So how do I check for that? How do I do this? Well, let's just figure that out. Let's pick some value A. So I'm going to say that suppose A is in the open interval minus 1 to 1, and I want to look at the limit as x approaches A. Okay? I'm just going to choose random practice. Okay? We're going to get to that, and that's one of the things that's why we're interested. Well, it's one of the reasons why we're interested. That's why we're interested in this. So, how do I evaluate that limit? I have a limit of a difference. So it's the difference of the limits. And I'm going to be a little old school and work everything out. Okay, so a lot of you can kind of cut to the chase, but that's okay. So this is our rule number 2, right? The limit of a difference is the difference of the limits. The limit of 1 is 1. It's a constant function, right? So that's 1. I knew that was going to happen. Freaking out now. Okay, I have a little more time. Okay, so how do I deal with limits of roots? I'm going to stop the recording though, because at least I want to make